Okay, so in the previous two lectures, we have discussed about the phenomenon of Bose-Einstein condensation and the condition for the onset of the BEC. So we will just throw light on some of the equations that were borrowed during the derivations we have done in the previous two lectures, and also we will tell you something on how to obtain the relation between the number of particles in the ground state to that of the the total number of particles. So the relation with the critical temperature we have assumed in the previous derivation. We will just prove it during this particular session. Okay, so one thing that so you take all these things as simple notes for you to get clarity regarding how it was all done. So one thing you have to note is that for temperatures of the system which is below the critical temperature, the system of a non-interacting boson can be considered as a mixture of two different phases. Okay, for temperatures below critical temperature, a bosonic system can be considered as a mixture of two different phases. Okay, so we regard the condensed phase and the normal phase as two different phases. So one is a normal phase. So means a normal bosonic system with you can say that some Ne particles in excited state, where what is the specialty, that is E not equal to 0 and P is also not equal to 0. That is a property of particles in the excited state. Okay, and second one is a condensed phase. And what is specialty of the condensed phase? N0 particles or N0 particles are in the condensed space in the ground state. Condensed space means the particles will be in the zero momentum state or ground state. N0 particles in the ground state. That is what E equal to L or P is equal to what? 0. And we can represent this fact graphically. So graphically the variation of two quantities. So I'm writing a graphical thing. So I'm taking the quantity T divided by Tc along x-axis. T by Tc means the ratio of the temperature divided by the critical temperature. And let me take one particular value here. So one particular value here, the value of T by Tc is equal to 1. So what is my value of T by Tc equal to 1? It means that at this point the temperature is equal to the critical temperature. So means that to the left of this T equal to Tc means Bose-Einstein condensation can occur, and to the right of this one there is no Bose-Einstein condensation, that is above the critical temperature. So we can say that if you take along the y-axis, we are taking two quantities along the y-axis. One is, this is a very standard graph that you can find out in reference books. That is, one is Ne by En. So that is Ne by En is taken along. This is a fraction. Okay, the graph quantities are represented as a fraction. Ne by En. What is Ne by En? Number of particles in the excited state to number of particles in the ground state. Okay, and also we are showing another fraction, that is N0 by N. N is the total number of particles. So that is shown in the y-axis. So we can say that these two fractions, Ne by N and N0 by N, are two complementary fractions. What is by complementary fractions? Means the total of these two fractions will be equal to 1, right? Because okay, when you sum it up, it will be equal to Ne plus N0 by N. Ne plus N0 by N means what? Ne plus N0 is N. So that is 1. So the total of these two fractions will be equal to 1, which means that when one of this fraction increases, the other fraction must decrease. That's what we mean by complementary fractions here. So the variation of complementary fractions with the temperature, when you show that, you can see that the variation will be like this. So see that this is the variation. Like what will happen below critical temperature, as we have discussed here, below critical temperature, T less than Tc, there will be two phases. One is the normal phase and other one. So what will happen is that this one above critical temperature, that is the normal phase. Okay, so the normal phase is this one. So this is normal phase. This represents normal phase. Okay, so Ne by N will be, this is Ne by N graph with T by Tc, and you will see that just as temperature, I have to draw from higher temperature to lower temperature. So as the temperature goes below this particular critical temperature, what happens? The number of particles in the excited state should decrease. Okay, number of particles in the excited state should what? Decrease. Why? Because these particles should be more and more getting just what? Piled up to what you call the ground state. So Ne by N will be getting decreased. And when Ne by N decreases, what will happen? What will happen to the other one? The other one should what? Increase. Okay, so we can see that the other one is just going like this. So when one okay, you can just see that I must draw from here actually. So this is where I have to draw actually to this side, and this is to this side. Okay, then only you can see that one is increasing and the other one is what? Decreasing. So I discuss it when okay, looking from this side. When you move towards lower and lower temperature, you can see that the particle. So this is this graph is for N0 by N. N0 by N. So it means that as the temperature is lowered, what happens? Number of particles in the ground state will be getting increased. Okay, and at T equal to 0 Kelvin, if you take that this is T equal to 0 Kelvin, or okay, think what will happen? See, all the particles will be in the ground state. That's why Ne by N fraction will be becoming equal to 0 at the lowermost temperature. Okay, so we can say that this is the representing the condensed region or condensed phase. So below T equal to Tc, okay, this is the condensed phase and this one is the normal phase. Okay, so this line represents the normal phase. Okay, that is one thing. Now another thing okay, you have to see is that regarding Bose-Einstein function that we have been using throughout our discussion now. So the Bose-Einstein function okay, is expanded as a series. So usually we say G nu of Z. Nu is known as the order of the Bose-Einstein function. G nu of Z can be expanded as a series function in terms of the gamma function. So it is equal to gamma of nu 1 by gamma of nu. Then integral from, there are several ways in which the Bose-Einstein function can be expanded. This is one standard way. Integral from 0 to infinity. You need not memorize all these functions, but only for your knowledge, I'm telling you this one. X raised to nu minus 1 dx. This is the definition of Bose-Einstein function. Okay, divided by z raised to minus 1 e raised to x minus 1. So this is the definition of, or this is the expansion of the so-called Bose-Einstein function, which we have been writing in two orders. One was we used G 5 by 2 of Z in our equation state. Another thing is we wrote G 3 by 2 of Z. Okay, so this 5 by 2 and 3 by 2 was in place of this nu. Okay, and Z is the fugacity. It's a function of fugacity. Okay, so when you expand this one, okay, and rearrange by using gamma values, you will be getting this is equal to finally Z plus, it can be expanded as a series, Z square by 2 raised to nu plus this is 2 Z cubed by 3 raised to, sorry, Z cubed by 3 raised to nu plus etc. it goes. Therefore, when you substitute, we have used a special value of G 3 by 2 of 1. So how do you get G 3 by 2 of 1? You substitute Z equal to 1. So it will be equal to 1 plus 1 by 2 raised to 3 by 2 plus 1 divided by 1 cube is 1 again. 1 divided by 3 raised to 3 by 2 plus 1 divided by 5 raised to 3 by 2. It goes on. Plus, plus, plus. It goes on. And you can see that this 1 plus all these quantities, when you put together, you will get this is roughly equal to, what will be the value of this one? G 3 by 2 of 1. I told you it is a converging series. Its value is equal to 2.612, which is the maximum value that G 3 by 2, okay, of Z can have. Maximum value. Okay, the reason is that for Z max equal to 1 for bosons. Hope remember that the value of bosons Z max is what? 1. That is the thing. And this value is also equal to the value of the Zeeman Riemann zeta function, which is zeta of 3 by 2. This is also equal to Riemann zeta function, zeta of 3 by 2. Okay, so this is the value that we have used in the derivation of condition for what you call condition for the onset of BEC. That's one thing you have to remember. Now another thing. So these are only for your own understanding. You can just read it and try to understand. No need to memorize everything there. Then one thing more, we have seen that there is a limiting value for the chemical potential for boson. I told you the chemical potential mu for bosons is either 0 or negative. Okay, that is the specialty of bosons. And how come that? So for that, let's go to the mean occupation number. Okay, from previous module unit, theory of simple gases, we obtained the mean occupation number for bosons. Mean occupation number for bosons we obtained, that is equal to 1 divided by e raised to, is not, okay, alpha plus beta e, and also which can be written also as beta into e minus mu, beta into e minus mu minus 1. Okay, beta into e minus mu minus 1. Okay, so how come this particular thing? You can just try to rearrange the mean occupation number equation, right? So you know that this n must be non-zero. It must be non-zero even for e equal to 0. Okay, even when energy equal to 0, this mean occupation number should be what? Non-zero. And it cannot be, you know what's mean occupation number? Mean occupation number is the average number of particles per energy level, right? So it cannot be 0, or it cannot be negative, and it cannot be negative, and it cannot be negative. It's an argumentative result. It cannot be negative. Mean occupation number negative means there is no meaning for that. Therefore, what does it mean? It cannot be negative means you can see we have to look at this particular expression, that is e raised to minus beta mu. You substitute e equal to 0, then e raised to minus beta mu should be greater than or equal to 1, is not? If it is less than 1, of course it is n is going to be negative, so it should be greater than or equal to 1. So what's the meaning? It means that mu, how can this be greater than or equal to 1? That is mu should be less than or equal to 0. Okay, so that is a logical conclusion for bosons. Okay, and when mu equal to 0, okay, which we already have seen that just it happens every time for photons, and it can happen when the temperature is going less in the case of bosonic condensation of any other bosons. Okay, Z is equal, when mu equal to 0, Z is equal to, Z is equal to e raised to minus alpha, which is what? E raised to mu by kt. Okay, so mu is equal to 0, then Z becomes equal to 1, and that is equal to what? Maximum value of Z max. Hence G3 by 2 of Z, which we have calculated, has a limiting value, for Z equal to 1. So these are the discussion that we have used, that is G3 by 2 of Z is equal to 2.612. So it has got a limiting value. That is another idea that you have to keep in mind. And finally, let's show that, okay, so another note to show that, this also I guaranteed, to show that n0 by n, that was question number 12, n0 by n is equal to 1 minus t by tc raised to 3 by 2. This also can be proved. Okay, so how to prove it? So for that we will just use certain equation that we have already derived. We have a Tc, the critical temperature, is equal to h square divided by, I'm doing it fast, so because it's all okay, 2 pi mk into n divided by Vz3 by 2 raised to 2 by 3. Okay, that is by equation number 11. Therefore, on rearranging, you can get V is equal to N divided by, okay, so I'm taking this V, that is equal to N divided by zeta of 3 by 2. Just you rearrange it by okay, taking cube and then taking square root. That's what you're going to do. Okay, that will be equal to into h square divided by, on cross multiply, 2 pi m k t c, okay, all raised to what, 3 by 2. So it will, okay, let me say call this one some equation by A or something like that. Also, you have got n is equal to n0 plus ne, which is equal to n0 plus ne. You have got an equation from equation number 8. Okay, what is that? V into 2 pi m k t raised to 3 by 2 divided by h cubed into zeta of 3 by 2. Okay, so that is maybe let's call it as equation number B. This is actually equation 8 in our previous derivation, right, from using. So I can now substitute, that is equal to n0 plus, okay, we will substitute for V here. So this V can substitute from equation number A. So what will happen, that one, that is n divided by zeta of 3 by 2. So there is zeta of 3 by 2 here. Then into h square by 2 pi m k t c, okay, whole raised to 3 by 2 into, already there is this particular thing, that is 2 pi m k t by h cubed whole raised to 3 by 2 into zeta of 3 by 2. So many of the things will be getting cancelled. Okay, so what happens is zeta of 3 by 2 straight away getting cancelled with zeta of 3 by 2 here. Then what is there, this h square raised to 3 by 2, that's okay, same thing here, denominator by h cubed, okay, raised to this one, so that will be getting cancelled. Then 2 pi mk 3 by 2, okay, so you can just see that will be also getting cancelled, right? So how can this particular thing, see that here I have to write h square when I take it to inside this 3 by 2, okay, I have to take h square raised to 3 by 2. So that is how h square is getting cancelled here. All other things, so what remains here is that tc is here raised to 3 by 2 here, and t is here raised to 3 by 2 is here. So what is that remaining? That is n0 plus n into t by tc whole raised to 3 by 2. Is it right? Okay, therefore, which you know what you have to do. Therefore, I can say n naught equal to, okay, n naught equal to, I am taking the other factor to the other side. So n minus n into t by tc raised to 3 by 2. So can you take that n as common factor? So that is equal to n into 1 minus t by tc raised to 3 by 2. Okay, so you take therefore n naught or n0 by n, we are going to the fraction, that is equal to 1 minus t by tc raised to 3 by 2. And this was the expression that we had to prove. Got it? Okay, remember, which is, this equation is applicable only when the temperature is below the critical temperature. Okay, means the BEC should be happening, and we have seen that what is the relevance of this equation. This equation helps us to understand the Bose-Einstein condensation better. That is, as T tends to 0 Kelvin, N0, T tends to 0 Kelvin means what? What will happen? So this numerator will be tending to 0 Kelvin. So 1 minus 0, that is N0 by N is tending to 1, or N tends to N0. That is all at 0 Kelvin, as per theory, all bosons must pile up okay, to the ground state or zero momentum state at absolute zero of the temperature. So that's about the Bose-Einstein condensation phenomenon, as well as the condition for the onset of Bose-Einstein condensation. And as far as your topics are concerned, give due relevance to this particular topic, because there is such a very important thing. And there is a topic on the experimental achievement or experimental observation of the Bose-Einstein condensation, and that topic is mentioned in your syllabus as BEC in ultra cold atomic gases. ഇങ്ങനൊരു ടോപ്പിക്ക് നിങ്ങളുടെ സിലബസിൽ പറഞ്ഞിട്ടുണ്ട്. സോ ദാറ്റ് ഈസ് റിഗാർഡിംഗ് ഹൗ Bose-Einstein condensation was first experimentally observed. I told you it happened almost after 70 years of its first prediction. Okay, ഏകദേശം 70 വർഷങ്ങൾക്ക് ശേഷം Bose-Einstein condensation എന്ന് പറഞ്ഞൊരു ഫിനോമിനൻ നടക്കാനുള്ള തിയററ്റിക്കൽ പോസിബിലിറ്റിയെ പറ്റിയിട്ട് പ്രെഡിക്റ്റ് ചെയ്തതിന് ശേഷം 70ഓളം വർഷങ്ങൾക്ക് ശേഷമാണ് കെറ്റർലി എന്ന് പറയുന്ന സയൻറ്റിസ്റ്റ് എന്ത് ചെയ്യുന്നത്, ഈ അൾട്രാ കോൾഡ് റുബീഡിയം ആറ്റത്തിൻ്റെ ഒരു സിസ്റ്റത്തിനകത്ത് ഈ Bose-Einstein കണ്ടൻസേഷൻ ആദ്യമായിട്ട് അച്ചീവ് ചെയ്യുന്നത്. അതൊരു നാനോ കെൽവിൻ്റെ ഓർഡറിലേക്ക് ടെമ്പറേച്ചർ കുറച്ചപ്പോഴാണ്. ഇനി എന്തുകൊണ്ട് ഇത്രത്തോളം ഗ്യാപ്പ്, തിയറിയും എക്സ്പെരിമെൻ്റൽ കൺഫർമേഷൻ തമ്മിൽ വൈ സച്ച് എ വൈഡ് ഗ്യാപ്പ് ബിറ്റ്വീൻ ദ ടു? അതിന് കാരണം ഇത്രയാണ്. ഈ നമ്മളിവിടെ എല്ലാം പറഞ്ഞിരുന്നത് എന്താണ്, അറ്റ് സഫിഷ്യൻ്റ്ലി ലോ ടെമ്പറേച്ചർ പറഞ്ഞുകൊണ്ടേയിരുന്നു അല്ലേ. ഈ ലോ ടെമ്പറേച്ചർ 0 കെൽവിനോട് അടുത്തുള്ള ലോ ടെമ്പറേച്ചർ അറ്റൈൻ ചെയ്യാൻ സഹായകമായിട്ടുള്ള എന്താണ് ടെക്നോളജി, അഡ്വാൻസ്ഡ് ലോ ടെമ്പറേച്ചർ ഫിസിക്സ് നമ്മൾ വിളിക്കുന്ന പേര് നിങ്ങൾക്ക് അറിയാം, ക്രയോജനിക്സ് എന്നാണ്. ക്രയോജനിക്സ് എന്ന് പറയുന്നത് വളരെ അഡ്വാൻസ്ഡ് ആയിട്ടുള്ള ഒരു തെർമോഡൈനാമിക്കൽ ടെക്നോളജിയാണ്. ഈ ക്രയോജനിക് ടെക്നോളജി ഡെവലപ്പ് ചെയ്യാൻ വേണ്ടി എടുത്ത കുറേ വർഷങ്ങളായിരുന്നു ഈ 70 വർഷങ്ങൾ എന്ന് പറയുന്നത്. അപ്പോൾ ക്രയോജനിക്സിൻ്റെ ഡെവലപ്മെൻറ്റ് ആയിരുന്നു, അല്ലെങ്കിൽ ലോ ടെമ്പറേച്ചർ അച്ചീവ് ചെയ്യാൻ പറ്റാതിരുന്നതാണ് Bose-Einstein കണ്ടൻസേഷൻ എക്സ്പെരിമെൻ്റലി കിട്ടാതിരുന്നതിന് കാരണം. അപ്പോൾ ഈ ഇദ്ദേഹം കെറ്റർലിയൊക്കെ ചെയ്തത് എന്താണെന്ന് വെച്ചാൽ അൾട്രാകോൾഡിന് വളരെ തണുത്തുറഞ്ഞ ആറ്റമിക് ഗ്യാസ് റുബീഡിയം ആറ്റത്തിലാണ് ആദ്യമായിട്ട് കണ്ടുപിടിക്കുന്നത് എന്നാണ് എൻ്റെ ഓർമ്മ. ഓക്കെ, സോ അങ്ങനെ ഇത് ചെയ്തതെന്ന് വെച്ചാൽ ദേ യൂസ്ഡ് വാട്ട് ഈസ് നോൺ ആസ് എ ലേസർ കൂളിംഗ് ടെക്നിക്. laser cooling technique to obtain this particular Bose-Einstein condensation. ഓക്കെ, അതിൽ എന്താണ് കൗണ്ടർ പ്രൊപ്പഗേറ്റിംഗ് ആയിട്ടുള്ള കുറച്ച് ലേസർ ബീമുകൾ ഉപയോഗിച്ചുകൊണ്ട് അവർ എന്താണ് ഡോപ്ലർ ഫിനോമിനൻ കൂടി ഉപയോഗിച്ചുകൊണ്ടാണ്, അല്ലെങ്കിൽ ബാക്ക് കിക്കിംഗ് ഉപയോഗിച്ചുകൊണ്ടാണ് ഈ ഒരു സിസ്റ്റം ഉണ്ടാക്കിയെടുത്തത്, അല്ലെങ്കിൽ ഒരു തണുപ്പുണ്ടാക്കിയെടുത്തത്. അതിൽ ഈ ആറ്റംസ് Bose-Einstein കണ്ടൻസേഷൻ കാണിക്കുന്നതായിട്ട് അവർ കണ്ടെത്തുകയും ചെയ്തു. ഇതിനെ പറ്റിയിട്ട് നിങ്ങൾ ജസ്റ്റ് റീഡ് ഓൺ ദിസ് വൺ ടോപ്പിക് ഇങ്ങനെ കൊടുത്തിട്ടുണ്ട്. ഇഫ് യു വാണ്ട് ഐ ക്യാൻ ജസ്റ്റ് ഗിവ് യു, ഐ വിൽ അപ്ലോഡ് ഇൻ ദ ഗൂഗിൾ ക്ലാസ് റൂം എ ലെക്ചർ നോട്ട് ഓൺ ദിസ് Bose-Einstein കണ്ടൻസേഷൻ എക്സ്പെരിമെൻറ്റ്. ടോപ്പിക്കിലുള്ളതുകൊണ്ട് ഞാൻ ജസ്റ്റ് മെൻഷൻ ചെയ്തു എന്നേ ഉള്ളൂ. So you can just refer to that one. If any doubt persists, if time permits, we will have a lecture on that particular topic also. And there are a number of videos on that one also, YouTube videos, so you can refer to that one. Okay, so that's about the Bose-Einstein condensation phenomenon. Now we are left with only one topic in ideal Bose systems, which is nothing but the Planck's derivation of the Planck's law of radiations, okay, by using bosonic principles. Okay, that we'll be doing in the next lecture. Thank you.